Swayam Prabha. Digital India. Educated India.
Good morning to all of you. Very happy to see so many young students. Actually, I have not given any talk to students for nearly 20 years. Students of your age. Then Dr. Jagan Mohan and Venkatakrishnan asked me to give you a talk some 10 days back. Then past 1 week or so, I have been thinking what to talk for all of you. You are very enthusiastic, highly motivated. So it is very difficult actually to talk to many of the young children now. Anyway, what I thought was the following. See, chemistry, all of you know, has three major components: organic chemistry, inorganic chemistry, and physical chemistry. And although this division is there, it is more artificial. Today, one has to know all the three to make any progress in research work. So, this division is mostly artificial and not natural. But I had my MSc degree from Madurai Kamaraj University more than 3 decades ago in physical chemistry. So my own emphasis will be on physical chemistry topics today. But it should not give a feeling that other two branches are less important. So what I have done today is the following. I have tried to give a feel for organic chemistry and inorganic chemistry to all of you, so that you will actually have a wider perspective. I will switch off the cell. So, I quickly give introduction for me. I had my MSc from Madurai University, then I did PhD from IITs Bangalore more than 3 decades ago. Then I went to Germany. I came here in 1993. From 1993 onwards, I am here. Now I am what is called as emeritus professor at the Department of Chemistry after superannuation. Right. During this period, my interest has been in electrochemistry and statistical mechanics. My own PhD degree was in electrochemistry and statistical mechanics. Interestingly, my own PhD guide didn't have a PhD degree. He had a degree in mathematics, which is a BA degree. But IIC invited him to become a professor, and he was there right till his retirement. So today I would directly go to the outline of my presentation. Right, the way I structured my talk today is the following. I would spend time on thermodynamics, efficiencies, functions, and applications. Why I did like that? Because in physical chemistry, we have 3 major components. What are they? Chemical kinetics, thermodynamics, electrochemistry. These 3 are the major topics that you see in any physical chemistry textbook. Others are there, they are equally important, but these 3 are the major topics. Other topics you see are polymer chemistry, solid state chemistry, and colloid, surface chemistry, interfaces, and so on. But these are extremely important because of the overlap with other subjects. So thermodynamics, kinetics, electrochemistry are very important because they are important to understand other subjects, whether it is surfaces or solid state or interface and so on. Right? So I divided my talk into 2 parts. First part, I would do more on thermodynamics. Then where I stop, I myself don't know. Then I will go to electrochemistry in second part. This is the way I am planning, so that there will be a link between the two. There will be a link between the part 1 and part 2. That's the way I structured my presentation. So I would spend some time on thermodynamic laws, transformations, functions and applications. You are allowed to stop me whenever you want, and I would not hesitate to answer to the extent possible. And all of you can also send email to me whenever. Email ID I will give shortly. So you can also send email to me when you have any query on any of these. Now, thermodynamics itself is highly interdisciplinary. For example, today, mathematicians, physicists, engineers, computer scientists, electronics people, all of them are making contributions to thermodynamics. How we will be seeing shortly. Then you have lot of foundations. Today you take up a book in thermodynamics at advanced level, it will look more like a mathematics textbook than like a chemistry textbook. The reason is you will see a lot of differential calculus, integral calculus, special functions, ordinary differential equation, partial differential equation, and so on. That means there is a strong mathematical foundations essential to understand thermodynamics. Then also you will see by its very nature, in chemistry when you deal with molecules, you have 10 power 23 molecules roughly. Then how do you understand their behavior? The only way you can understand is by statistical reasoning. So you need to have an assembly of particles and then see how they are distributed, at what energy levels, how they are going to contribute to the properties of a system. So that means by very nature, the statistical physics or statistical mechanics or statistical concepts will come in thermodynamics. Very amazing. Unless we know how the molecules are distributed, we cannot understand thermodynamics. So you need to have extremely good understanding of statistical laws. Probability, for example, Bayes theorem, conditional probability and so on. So all of them are extremely important. Then we say thermodynamics, but actually what we are studying thermostatics. That means what? We are studying time independent quantities. Thermodynamics means you should actually cover time dependent properties. Whereas what we are major part studying to 90% even at MSc level is only thermostatics. Why? Because the time dependence has not yet been understood. The time dependence of thermodynamic quantities is still at the beginning stage in terms of the advancements. So it is essential for us to restrict to time independent properties. Right? Then why this is very important to do this? Because our laws of thermodynamics tell you essentially that any process you carry out, efficiency cannot be 100%. That means you need to have some kind of a limitations in understanding how to carry out a process in an efficient manner. So it is here that all our first law, second law, third law will come. That means how do you carry out a process in an efficient manner? That is given as a rule. The thermodynamic laws actually have come out of experience. There are axioms. The proof is coming more by experiment. So originally when it was laws were given, they were given as postulates. And nobody has found exceptions to third law, second law, or first law. So they ought to be correct. Nobody has found exceptions to thermodynamic laws. Right? We will be talking more on the transformation shortly. Now quickly you tell me, sir, in one line tell me what does thermodynamics do? It does bookkeeping for energetics. How much you put input energy, how much you got energy back. It is an accountant job. It only does bookkeeping. So people say, what is your thermodynamics? After only bookkeeping. But that bookkeeping is essential to carry out any further advancements. So essentially it is a bookkeeping. Thermodynamics does bookkeeping of energetics. That's all it does. What energy you gave, what energy you got. How much energy you gave, what type of energy you give input. That's all it tells, nothing else. Right? Now, conventionally people have postulated 3 laws of thermodynamics. What are they? First law of thermodynamics, what does it tell? It tells that energy is conserved. That means you can convert from one form to another, but you cannot create the energy. So people call it as energy conservation, first law. Then first law, when it does finally with the total differential and so on, you get a new state function. Sir, what is state function? State function means it depends only on the initial and final states. It does not depend upon the path you chose. Right? So it's a state function. So first law gives a new property called internal energy. E or U, they give the symbol. When I studied, I was happy with the symbol E. Modern books are giving the symbol U. Right? So first law has given an entirely new concept called internal energy. Sir, tell me, what is this internal energy about? It is the energy that is present in that molecule, in a system. It can be solid, liquid or gas. So the energy that is present in a particular system internally is called internal energy. Right? So where from this came? This came from the combined first and second law of thermodynamics. Right? If I write the mathematical statement, you will see that this will come naturally. Right? Then when you go to second law, what does second law do? Second law essentially tells you, when you carry out a process, how much efficiency you can get. Is there a limit to the efficiency that you can get as a result of this transformation? Sir, what is transformation? It can be isothermal process, adiabatic process, isobaric process, isometric process and so on. Right? So you can carry out a process in any way you want. Then when you carry out such processes, which process has the maximum efficiency? That is given by the second law. Sir, tell me what process? Normally we say, if you carry out a process reversibly, it will have the maximum efficiency. Right? So that's what people say as the consequence of second law. Sir, how you can carry out any process reversibly? What they are essentially meaning is, you carry out a process so slowly that when you reverse the process again, you should come back to initial state. Then they will say it is a reversible process or quasi-static process. That's what they will say here, second law. Right? Then second law gives a new property called entropy. What is that? Entropy is nothing but a measure of disorder. If you find a compound having more magnitude of entropy, it means it has more disorder. More disorder means more entropy. That means what? Entropy is a measure of disorder. Right? Sir, suddenly your thermodynamics, how it went to disorder now? Because absolute entropy can be defined in terms of probability. Through that, we get the concept called order and disorder. That's how the entropy came to be related to order or disorder or probability. In fact, this definition was given by Boltzmann. Maxwell Boltzmann, actually he died very unhappily because people didn't realize the importance of the entropy and probability. The equation is given in his epitaph even now. You can see there, entropy is directly related to what is called the thermodynamic probability. Right? In some slide I have written how it exactly comes. So, this relation governing entropy and probability is solely due to Boltzmann. So, to honor him, we are given the name Boltzmann constant for that constant that appears in the entropy equation. S equal to K, Ln, W. That K is a Boltzmann constant. Ln is a log function, log to the base E. W is thermodynamic probability. So, Boltzmann definition is the one that gives this. Entropy can never be negative. Right, we can prove that because probability cannot be negative. So, entropy also cannot be negative. Entropy is always a positive quantity and greater than 0. Can never be negative. There is no process where entropy changes finally becoming negative. This is the statement of second law. Total entropy of the system and surroundings is either constant or increasing. It will never be decreasing. Right? That means always the universe is towards more disorder than more order. So, every time there will be more disorder at the end of the process for whatever process you do. Right? Then, that's a very good statement. Then, see, after they formulated all the three laws, they found 0th law. No, we are not defined 0th law yet. Already they have given first and second and third law. So, they found that when you define temperature, let us call it as the 0th law. Right? So, after they formulated the three laws, then they found that we have to define temperature. So, let us call it as 0th law. Essentially, thermodynamic equilibrium. Right? Then, first law says you cannot win, you can only break even. Break even means what? You cannot create energy. You can only transform from one side to another side. So, you can never win in terms of the energy getting, after you put some energy, again getting some energy back exactly is not possible. So, you cannot win, you can only break even. That means you can transfer from one state to another state, one form to another form. Right? And then they say this also you can do only at absolute 0 temperature. Right. So, even here only when you have absolute temperature only you can do that. Right. So, that is the most important thing. If you want to get 100% efficiency of any process, you can get it only when you get to 0 Kelvin. And 0 Kelvin can never be reached. That is third law of thermodynamics. That means any process we try to do, we can never get efficiency to be unity or 100%. Right? So, this was during the textbook by Walter J. Moore. This was the book that I followed when I was myself doing MSc in the 70s. Right? Okay. Now, I said first, second, third law of thermodynamics. What are the weaknesses of the three laws of thermodynamics? The weakness is, it is not telling anything about the time dependence of properties. For example, if you ask the question, sir, how much does inter-energy vary with the time? Or how entropy varies with time? You are not able to answer that. So, many people, including Prigogine, who was a Nobel laureate and all, they started formulating what is known as fourth law of thermodynamics, where they are giving postulate of how properties will vary with respect to time. Right? So, that is something that I want to tell. That is why I immediately came here. Right? Different facets of thermodynamics. What are they? Normally, our BTech students as well as MSc students will have all these three in their syllabus. We have classical thermodynamics, which consists of 0th law, first law, second law, third law statements. Very easy, we can always state all the three laws of thermodynamics. Then, when you do that, you are estimating properties. What a property? You can get enthalpy changes, entropy changes, Gibbs energy changes, Helmholtz changes, these delta G or delta F. So you can get property changes. That means what? I take a helium gas, let us see. I change the helium gas from 3 atmospheric pressure to 4 atmospheric pressure at 300 Kelvin. Then I can ask the question, what is the Gibbs energy change? What the entropy change? What the energy change, and so on. So I can take gas, liquid, solids, and so on, carry out a process, and then I can ask the question how the thermodynamic properties are changing. So all the applications of the classical laws only are going to give you how properties change when you carry out a transformation. Nothing else, right? So you can carry the process isothermally, adiabatically, and so on. Then you can get properties calculated, some kilocalories per mole, some kilojoules per mole, and so on. So classical laws end here. Then when you go to statistical thermodynamics, there what happens? You can ask absolute quantities, you can estimate them. Sir, I have 10 moles of argon and I want to get the internal energy of 10 moles of argon. I have gold, I want to get internal energy of gold, you can do that. I want entropy of nickel, you can get it. Whether you take solid, liquid or gases, it is possible to get absolute quantities, internal energy, absolute entropy, Helmholtz free energy, Gibbs free energy, enthalpy, specific constant pressure, constant volume, everything. That means if you want to get absolute quantities, you need to have statistical thermodynamics. Right? So, whereas there we can only get changes, here we can get absolute quantities. Right? So, to get the absolute quantity, you need a quantity which our statistical mechanics people call as partition function. What is that? It's a function that partitions energies. How does it partition? Translational, vibrational, rotational, nuclear, electronic, and so on. So, there is a function that partitions the total energy of a system into various components. Right? So that's an important thing now. That means if a molecule has only translational motion, then I have to only compute translational partition function, like an monatomic gas. They have only translational motion. So only I have to estimate translational partition function. Suppose a molecule has vibration, then I need to know vibrational partition function also. Right? So every molecule that you can give in nature, I can estimate the partition functions. Right? Once I estimate the partition function of any compound, all this I can compute. That's the amazing property of the statistical thermodynamics. Right? Now, all the information is contained in this partition function. Right? Essentially, it's a sum over the partition function. Suppose you want to ask the question, sir, what is partition function? We can say, is that equal to sigma e power minus beta epsilon I. Beta is 1 by kT. So, once you sum the energies of individual state like epsilon I for ith state, you will get the partition function. Then what happens? It has translational motion, then it will become Z translation, this will be epsilon translation. Z vibration, epsilon vibration. Z nuclear, epsilon nuclear. Right? So then you have to only get the total partition function by adding the individual thing. That's all. Right? So essentially, you know how you multiply e power, you know. E power x plus y is e power x into e power y. right? So Z will be Z translation into Z vibration into Z rotation, like that it will go, right? So total energy you have to add in the partition function, they'll get multiplied because of the property of the exponentials, right? So you know how you write, you multiply e power x into e power y, e power x into e power x plus y, right? So e power x will be separately one partition function, e power will be another partition function. So you multiply them to get the total partition function, right? All brilliant people have worked on many of these things, right? Yes. Beta is 1 by kt, where k is Boltzmann constant. Beta is 1 by kt, where k is Boltzmann constant. Boltzmann constant R by N, R is the gas Avogadro number. T again, remember, absolute temperature. You should not put the centigrade, all these things. Very important to know this, right? In fact, past 3-4 years, I am trying to work on a particular problem which is unsolved for several decades. There I am trying to compute the partition function for a magnetic system, and no one has done till now. It's very unsolved problem, more than 6 decades. There I am trying to get the partition function of a ferromagnetic and antiferromagnetic material. If you go to Google and give my name, you will see the papers all estimating the partition function of various magnetic materials. So, estimating the partition function today is a $1 million question for new materials and new systems. What they have till now done is the following. They have till now estimated only the partition function for ideal diatomic gases, polyatomic gases, and univalent metals and so on. So, estimating the partition function is a very challenging problem. 3-4 Nobel Prize already has come in this field. Estimating the partition function for metals and so on. I think I kept the slide there. Right. So, if you see here, you can do translational, vibrational, rotational, electronic. Then what will happen? Here you will put the corresponding energies here. That's all, nothing else. So, if someone gives me energy states directly, I can compute the partition function. But nobody is going to give you that. Today, if you are reading modern new literature, you will see there is a package called Gaussian package. Software is available. Our institute has bought it. Nearly 200 users are using it. What it will do, it will give you the coordinates of the molecule. This is my atomic weight, this electronic configuration. It will do extensive numerical analysis and gives you the molecule information. And using that information that is given by the what they call as a density functional theory, you can get the energies that you want. But there is no formula that it will give. It will only give numbers. Because it gives numbers, it has only limited use. If you want a molecule nickel property, you can give for nickel. Then again, when you find a new binary alloy, for example, it won't give. Right? That's a problem there. So, there is no analytical method of getting the information. Right? That is the problem with the packages that we are having in the computer center for Gaussian and many other variants of the software packages. Right? That is the important. But we can still get the numbers we want for any system. Then I will come to what is the non-equilibrium. All our thermodynamic properties when we compute, they are all actually essentially only the equilibrium properties. That means you will ask the question, sir, absolute entropy of a silver at 400 Kelvin, you will get. Then when you get the entropy change given initial and final states, you can compute from this. However, if you want time dependence, sir, how does entropy change with respect to time? Both of them cannot answer. That means your classical thermodynamics and statistical thermodynamics, both of them cannot answer the question how a system behaves with respect to time. And for chemists, it's a big weakness because we are following the chemical kinetics of a process. If we are not following time dependence of a chemical reaction, then it has no use for us. So we need to know time dependence. Then what happened? From 1960 onwards, people developed a new topic called non-equilibrium thermodynamics, or sometimes they call irreversible thermodynamics. What it will do? It will give you the time dependence of interenergy, entropy, Helmholtz energy, everything, by postulating the fourth law of thermodynamics. So you are able to get this time dependence using non-equilibrium thermodynamics. Right? Already 2-3 Nobel Prizes have come in this. Right? Then when you want to see the progress of a chemical reaction, right, then you need to apply concepts from non-equilibrium thermodynamics. For example, you can ask how interenergy will vary with time. So dE by dt. How enthalpy will change with time. How entropy will change with time. Right? So you can ask all these only from non-equilibrium thermodynamics, which you cannot do by classical and statistical thermodynamics. Right? So now when you ask ds by dt, there is a name for this. The name is rate of entropy production. So ds by dt is called rate of entropy production. Obvious, like your chemical kinetic dc by dt, rate law. Entropy with respect to time. How entropy changes with respect to time is ds by dt. Right? Then this is a total entropy change of a system. What is ds? Total entropy change of a system. That can be written as two contributions. What are they? DES and DIS. What is DES? Entropy change due to interaction with external surroundings. DES is nothing but entropy change of a system due to its interaction with external surroundings, E. Sir, why are you emphasizing that? If you carry out a process reversibly, this DIS will be 0. So this contribution will come only when you carry out a process irreversibly. Then what is fourth law of thermodynamics? Fourth law will tell you this DIS can only be greater than 0. Right? So there is no process where DIS will become less than 0. Whereas the DES can be equal to 0, less than 0, greater than 0, but this can be only greater than 0. That's a postulate of non-equilibrium thermodynamics. Right? Very, very important for us to know this. Right? Any doubt till now, you can feel free to ask. We'll give you a few minutes gap. Anyone till now, any doubt is there? Don't hesitate.
Sir, can DIS be 0?
Yeah, DS will be 0 only when you carry out a process reversibly. That means any process when it is carried out reversibly, this DIS, what's the name for this? Entropy change due to irreversible nature of the process. So when you carry out a process reversibly, this term will be 0. Right? That's it. And to get maximum efficiency of any process, you should carry out a process reversibly. And that is not possible because every process we cannot guarantee it will be reversible. Feel free, any other doubt till now you can ask. Don't hesitate. Any other doubt? If If you don't ask, I will ask at the end. Any doubt till now? Okay. So we'll go to next. See, chemists are very much concerned about one important quantity, which is the Gibbs free energy. Right? See, normally chemists in general are obsessed with the quantity Gibbs free energy. Why? It is the one that is going to govern the occurrence of a chemical reaction. That means the delta G will predict thermodynamic feasibility of a chemical reaction. That means if delta G is negative, the reaction will occur. If delta G is 0, reaction is at equilibrium. There is no process where delta G is positive. It is thermodynamically forbidden to have delta G positive. So, for every reaction that occurs, the Gibbs energy change should be negative. That means what? Delta G should be negative. For any reaction to occur, delta G has to be negative. There is no react process where delta G will be positive. Only if delta G, sir, what is delta G? Tell me. G of product minus G of reactant. That means if I want to know what is delta G, it will be G of products minus G of reactants. Right? What is G? Gibbs free energy itself. So, if I write a reaction, let us say H2 plus O2 giving H2 or something, then G of product minus G of reactant is delta G. That means I should know what is the G for product and what is the G for reactant, then subtract it. Then, sir, who is going to give me the G value? We have handbooks available. The handbook of chemistry and physics is there for the past 40-50 years. They keep on updating. When they find a new material, they will give G for that substance. It can be solid, liquid, gas, binary alloy, ternary alloy. It can be nanomaterial, anything. For every time, there is a method to get these quantities. So once you get these quantities, you will be able to get the change in Gibbs free energy. Right? So delta G is the one that chemists are obsessed with that. Many of you know Van-Hoff equation and all these things. You will get what is known as the reaction quotient. Le Chatelier's principle, for example. What you will do, you will perturb a system at equilibrium and ask the question how the system responds. So that is given by the reaction quotient. That means delta G be written as delta G naught plus RT ln Q, something like that. So you will be able to predict how to make delta G negative by changing the reaction quotient or temperature. Right? That's a very important thing. Then also there is a relation between G and affinity. What is affinity? Affinity of a reaction is related to chemical potentials. Right? Affinity is related to chemical potential. Sir, what is chemical potential? It is the potential existing in a chemical to carry out a reaction. See, chemists have always beautifully thought of these things. It's the potential that exists in a chemical to carry out any process. What's the potential of so-and-so winning the Olympic medal? Like that. Same way, what's the potential of helium to carry out this process? What's the potential of this substance to carry out this process? That is called as the chemical potential. Right? So, chemical potential tells you the potential that exists in a compound to carry out something. That's a chemical potential. It is directly related to affinity of a reaction. Right? Then, if you ask the question, sir, how chemical reactions occur? They occur on account of affinity. What is affinity? Chemical potential. All are interlinked. They are not divergent topic. All are converging to finally to chemical potential. And if you see in my part 2, I'll be talking electrochemical potentials. What is that? When you have charged species, lithium ion, sodium ion, bromide ion, all these things, there will be electrochemical potential. Then when chemical potential will come, it will come for neutral substances. If you have neutral substance, you will have only chemical potential. You have a charged species, electrochemical potential. Right? That also will come in second part. Then, like I said, there's a book by Prigogine with the title Thermodynamics. What it tells you the following: he was a Nobel laureate. He has given how this topic is very important for further understanding of thermodynamics. Right? Then you have absolute entropy and its significance. The significance is entropy is a measure of disorder. If you have more disorder, it has more entropy. Sir, when entropy will be zero, if all the molecules are in the lowest energy state, then there will be disorder will be zero. If disorder is zero, entropy will be zero. Amazing, right? So when all are in the same lowest ground state, probability will be 1. Ln1 is 0, so absolute entropy is 0. So whenever you have all the molecules occupying the lowest energy state without any disorder, entropy will be 0. So when it will happen? 0 Kelvin. When you have 0 Kelvin temperature, all the molecules will be in the lowest energy level without any disorder, so entropy will be 0. Right? That's the amazing thing about this. That is how we have statistical definition of entropy. Right? So, if you want, sir, give me an equation for that, the equation will be S is proportional to L and W, where this W is known as thermodynamic probability. Right? This constant is given the symbol K, and then okay, right? So if you see here, so suddenly how the log function came, we will see in the 1 or 2 slides later on how the log function came. But more important is this proportionality constant was found later, and because this was given by Boltzmann, they decided to call this as a Boltzmann constant. Right? Now, why it is called thermodynamic probability? Why not simple probability? Can anyone answer why it is called thermodynamic probability? Why not simple probability? Simply we are studied in the plus 2 or 10th standard and all, there is a probability, then you toss a coin, how many times heads will come, tail will come and so on. Toss a coin 10 times, how many times 5 heads, 5 tails will come, all of them we study in probability. Or throwing a dice, or playing cards, something. Now, why this is called thermodynamic probability? Any guess? Yes.
Entropy is something which can never be decreased. Like with each process, it keeps on increasing. So
Yes,
with
yes.
increasing number of processes, the probability of it being increased.
That is partially correct. That's partially correct, but more correct reason can also be there. Because even in the other way you are telling, there also when we toss a coin, probability can increase, decrease and so on. Right? So, yes.
Then does it depend on the system and how the molecules are arranged?
That is true. That is the way probability itself comes. My question is, we have given a separate name here called thermodynamic probability. Why I didn't call it simply probability? Very easy if you guess. You. Yes.
So the way that was probability of it increasing.
Correct. That's true. But W can be right. What you are saying is 99% correct only. Right. 99, yes. 99% correct. I tell you. No, that can happen even otherwise. Even if I remove it, the name thermodynamic, it can happen. Right. Yes. That's a correct answer. Normal probability will never exceed unity. Whereas here W always greater or equal to unity. Isn't it? Because this W is going to be a big number. Whereas normally when you toss a coin, you get probability 1 by 8, 2 by 15, 3 by 20 and so on. Whereas the probability is entirely different because the lowest value itself is 1. The value will be always greater or equal to 1 for W. Whereas there, W always there probably less than or equal to 1. It will never exceed unity in any system in probability normally. Normally when you find out the probability of tossing a coin, tossing 10 heads, 15 tails, all these, it is never higher than unity. Here, W can only be greater than or equal to 1. So people are given the new name called, this is thermodynamic probability. Right? Another method of talking about W is, it is also known as the total number of microstates. Those who are doing statistical mechanics will know it is known as total number of microstates. What is that? Arrangements of molecules in various energy level is called a microstate. Sir, tell me W, what numbers are 100, 200, 300, 400? So it's a big number. Right? That is why they are given a name thermodynamic probability. Plus, it arises only in thermodynamics, this particular concept. So it is called thermodynamic probability. Right? Okay. Now, normally we carry out a process either reversibly or irreversibly. Many examples are there. Like I said, according to second law of thermodynamics, only when you carry out a process reversibly, you will get maximum efficiency. How to prove that? You can prove by many methods. One is by Carnot cycle. Some of you may study later on or might have studied by now. We construct what is known as a Carnot cycle, where we can actually find the efficiency will be higher only when it is reversible, and efficiency can never be unity in any heat engine and any process. Right? That's the way the second law applications start coming now. Now, you quickly go to the applications. Right? What first law of thermodynamics does, essentially it calculates the energetics for various processes. Then, second law essentially tells you how to compute efficiencies. How do you define efficiency? It is the work done divided by the heat input. So, efficiency is nothing but work done in the process divided by the heat input, heat supplied to the system. That is known as the efficiency in this context. Thermodynamic efficiency is nothing but the work done divided by the heat input. Right? So, we can compute this efficiency for many processes using second law of thermodynamics. Right? So, third law will tell you how to compute the entropy. Right? So, there is a method by which you can calculate absolute entropy, both by statistical mechanics as well as by third law of thermodynamics. Right? Now, this is what I will quickly tell. Now, if you see here, when you ask the question DIS, this is the answer. For a universal process, DS system plus delta S surroundings will be greater than 0. Normally in the BTech, that's normal, there will be a question on compute the entropy change of the system and surroundings for a reversible process like that. Then they should show that they are getting exactly cancelled and become 0 in a reversible process. They have to show that it is greater than 0 in irreversible process. So normally we have past 20-30 years we have been asking the question how to compute delta S for a irreversible process. They have to show that system and surroundings would be greater than 0 for irreversible process. So entropy change will be finally greater. Sir, what is system plus surroundings? It is called universe. System plus surroundings is nothing but universe. Normally we say anything except system is surroundings. Together they are universe. So delta S universe is greater than 0 or equal to 0. That means what philosophically? Philosophically it means disorder will keep on increasing the universe. It will never decrease. Disorder will keep on increasing in the universe. At the best it can become constant, but it will never decrease. That's the message of the second law of thermodynamics, right? Then you need to know what is the driving force for heat transfer, thermal gradient. Temperature gradient, if we bring out, there will be heat transfer. In a chemical reaction, it will be affinity or chemical potential. In the ion migration, it will be the potential gradient. In the diffusion, it is concentration gradient. So, the driving force for each of them is we can identify easily for any of this process. So, why suddenly you are going to this? Because this is the way we are going to calculate efficiency for non-equilibrium processes. At that time, we will need all these things. Right? That is the reason. Now, there are many statements of second law of thermodynamics. You can see that essentially all they are telling is the following. Essentially, they are telling that the efficiency can never be unity. It cannot by itself transform from one process to another process. Clausius has given these, Kelvin Planck has given, there is also Corot theory, geometrical statements, and then there is one given by the others. So, all of them essentially tells you that at the end, efficiency can never be unity. That's the more sum and substance of the second law of thermodynamics. Now, quickly we will see what is free in a free energy. If the energy freely available is called free energy. Sir, what is the meaning of freely available? Freely available to carry out a process is the free energy. That means the energy that is freely available to carry out your work is the free energy. Then you have two energies, one is the Helmholtz, one is Gibbs. This is the Helmholtz free energy, this is the Gibbs free energy. Right? Then you can relate the dF to work done in isothermal expansion. We can prove that the dF will be equal to minus W or plus W. That means we are relating the free energy to work. Very amazing. This comes from the chemistry. Delta F. And suddenly we can relate it to work done in isothermal expansion. What does this mean? It means the energy freely available is used to carry out work in isothermal expansion. How the chemistry suddenly got linked with the thermal process, which is the isothermal expansion. Then electrochemistry is very important for us. Delta G is minus NFE, where E is electrode potential, F is Faraday, N is number of electrons. Day in and day out, electrochemists spend time only on this. Delta is equal to minus N of E. That means we linked thermodynamics and electrochemistry. Suppose tomorrow you find a new compound and you want to find the delta G or G for that process. All you have to do is construct an electrochemical cell and measure the electrode potential using voltmeter, then you will get delta G. Amazing. Whenever you find a new compound, you want to get thermodynamic properties, all you have to do is construct appropriate electrochemical cell, measure electrode potential and then get delta G. From delta G you can go to G easily, which I will show. So, anyone finding a new compound tomorrow, they have no way from escaping doing electrochemical measurements. Only if you do electrochemical measurements, you are going to get thermodynamic quantities. This is the power of electrochemistry. You see, everywhere battery powered vehicle, fuel cells, supercapacitor, everything. Mainly because of this property. Namely, you can find out construct a new material, invent it, get delta G, you will know what's the efficiency, is it worth trying that further? Whether the compound that you invented newly, is it worth investigating further? That is given by this equation. Delta G has to be negative. So, the more negative is good for you. More negative means your E should be very, very large. Positive. N should be very large. N is number of electrons transferred. You cannot give 10, 20, 40 electrons and all. Transferred in a material. So this you don't have big control. Your control is only in this electrode potential. Right? This is the power of the electrochemistry. Right. So this we will do in the second part when we are again meeting after 5 minutes. So assemble after 5 minutes. And I'll give my email ID. Those who have some doubt, you can always approach me through email. iitm.ac.in. Any doubt regarding this topic or any topic in physical chemistry, you can approach me. I will, if I don't know the answer, consult my colleagues and tell you. So anything in physical chemistry, you are allowed to approach me whenever you want through email. Feel free. It is something should be useful to all of the participants. So I always see that the participants should get benefited by attending all these lectures. Right? You take this as opportunity to interact with all the faculties of our department. Right? We will be more than happy to assist you where whatever be the type of assistance you will need. Right? Our aim is essentially like our director keeps on telling, to make IIT inclusive to everyone. Everyone should get the benefit of IIT faculty and infrastructure and facilities and expertise. So no need to hesitate. It is a very free, open system. No one will scold why you send the letter, why you send the email. So you are allowed to approach all of us. There is no, there should be no inhibition on your part. On our part, we will be more than willing to assist. It can be experimental measurement or new compound. It can be a new idea. New idea, if you are always allowed to approach us, we will give all the facilities to carry out and verify. Right? So what we will do now, it is 10:05, 10:10 again we will meet. And 10:10 I will go to second part, right, after spending a few minutes on this.